Okay, we're going to try this YouTube explanation of the Chapter 7 test. You are being asked for the mass of the Earth, and you're given stuff like the force that a certain mass has. Okay, we have a we also know the radius of the Earth right here, which is a given right there. And we know the value for capital G, which is the gravitational constant, which is what Cavendish found. So that's a given. It's on the board. You can have it anytime you want. So is the mass of the Earth, frankly. This is the radius of the Earth. The mass of the Earth is also on the board, but that's what we're proving right now. So I know we know the answer, but we're proving that's the answer at this point. So your equation is F equals G times mass of the first object times mass of the second object over the radius of the Earth squared. I solved for one of the masses, it doesn't matter which one. Mass of the Earth equals force times radius squared over G times the other mass. I'm going to put in the other numbers. I said F was the force being used here that came from this mass here. So the force times the radius squared, sorry guys, the radius of the Earth squared. Over the value for G, G is just look it up. And the mass of the other object that's not the Earth, and we were told is 5.5 kilograms. So we're going to take this number times this number squared. I suggest that you do this number squared first. This number squared times this one, divided by this one. And the mistake that I've seen is then people are typing times 5.5. Just keep going. I don't even hit equals and say divided by 5.5. When you finally hit equals, you should get 5.9 times 10 to the 24th. And the unit for that is kilograms. We had a big discussion on how the units work there, so I'm not going to repeat it at the moment. If you want to come and ask me to do it, I will. But I know that mass is in kilograms, and as I said, I already had a big discussion on how they cancel out on the board. We're being asked to calculate the orbital period of Mars in Earth years. Well, the comparison between two things that are orbiting a central point that are operating in the same gravity field is the time of the one object, that's Mars, over the time of the other object. Well, what's the orbital time for Earth? It's a year. All that is squared. It's equal to the radius of the first object, which is Mars, and make sure that Mars and Mars are on top. This is the radius of the orbit for Mars. This is the radius of the orbit for Earth. They told us that right there. And I had to convert this from 228 million kilometers to 2.2 meters. You have to convert it to meters by putting on 3 zeros. That's times 1,000. This with 3 more zeros is meters. And then put it in scientific notation. This divided by that to the third power. Please go test your calculator and make sure you know how to do to the third power. And do you actually get this number? I moved the unit years over. 1 year squared is 1 year squared. 1 squared is 1, year squared is a year squared. So times 1 does nothing to the number, and the unit is years squared. And it's equal to time of Mars squared. This is going to need to be square rooted, but of course I have to do equal things to both sides, so I have to square root both sides. Years squared becomes just years. And this number square rooted is 1.87. And I've solved for time of orbit, for Mars. Okay, talking about the geosynchronous satellites, we need to find the distance from the core of Earth. It says that it's 35,786 kilometers altitude over the equator. That's not the distance from the core, that's the distance from the surface. And I'm going to have to add it to the distance from the core. Here's the distance from the core to the surface. Remember back from problem 1. So distance from the core to the surface plus distance over the surface. Now, if I'm going to add up these numbers, they have to both be in the same times 10 to the number. They have to both be E6. And they have to be both in either meters or kilometers, and the E number has to match. So I decided to make a match by taking the kilometers to meters and then making that number into E6. So kilometers becomes meters by sticking 3 zeros on it. That's multiplying by 1,000. Then I moved it the decimal 6 spots over. And I know that's not true scientific notation, but I have to have it in E6 meters. So it's 35.786 E6 meters. Then I can add them up. This now is the distance from Earth's center for the satellite. Now, the time for the satellite is equal to 2 pi times the square root of the radius cubed over that g constant times the mass of the Earth. And again, that's not a secret, it's just on the board. You can have it anytime you want. You don't have to memorize it. So the time for the satellite should be about 24 hours, right? It's geosynchronous, it's staying in one place in the sky. We had a big discussion with some videos about why it's not exactly 24 hours. Your answer should actually be slightly less than 24 hours. Okay, so here's my radius above the core of Earth, cubed, over that value for g, which again is not a secret, it's on the board, times the mass of the Earth, which is on the board, frankly, and we figured out back up here anyway. So take this number to the third power, divided by this, divided by that. I suggest you hit pause and actually try it out and see if you're getting the same answer. 1.880 times 10 to the 8 seconds squared is the units, by the way. I need to take the square root of this and then multiply it by 2 times pi, and that will give me 8,598.8 seconds. That's not really a very good answer, though, because it's hard for anyone to imagine that in seconds. We don't work in seconds in that kind of time span. So it's 3,600 seconds per hour. So if we divide it by 3,600, we will get hours. And I got 23.89 hours. At least it's close. What's the orbital speed of a geosynchronous satellite? The time for the satellite, the velocity of the satellite is square root of g times mass of the Earth over r. G is that same number, 6.67 e negative 11. Just put that in. Mass of the Earth is also a given, which we had from the last problem, over the radius above the core, which we figured out back here. Not above the surface, above the core, the center of mass of the Earth. It's this times this divided by that. I would hit pause and see if you can punch that in properly and get the same answer. Then take that number and square root it, and I got 33,505.7 meters per second. Five, what height of orbit above Earth's surface does a satellite need if it were to experience 1/10 the gravitational force that it does on the surface? Okay, so the distance from the core on the surface is this. Remember Earth's radius, we've used it twice at least already. This is the distance from the core, from the center of mass. Now, the equation that uses that is, remember this one? G is a constant. The mass of the satellite is constant. The mass of Earth is constant. So for the purposes of this problem only, we can cross this out and say, that's not going to change. And I'm only concerned with the change here. I want to change the force so that it's 1/10 what it was before. Well, I need to divide it by 10. Whatever it was before, I need to divide it by 10, which means this R needs to be the square root of 10, because square root of 10 squared is 10. So I want R to be square root of 10, so that when I square it, it turns into 10. Here's the square root of 10 meters. So this is how far it was if it's on the surface. I need its square root of 10 greater than that. So take square root of 10 times the radius of the Earth, or distance to the surface, same thing. And we have meters from center. But I want what height of orbit above Earth's surface. So I have to subtract out the distance from the core to the surface. But to do subtraction, I need the e's to be the same. You could fix either one. It doesn't really matter, as long as they're the same when you get done. I chose to go fix this one so that it's times 10 to the 7th. I need this number to go up. Therefore, the decimal must get smaller. It must go here. That gives me 0.6838 times 10 to the 7th meters. So this is the distance to the satellite from the center. This is the distance from the center to the surface. My answer will be, it's an m, meters from the surface, which is what I was asked for. What height of orbit above Earth's surface does a satellite need? Six, two identical satellites were put into orbit. Their center of masses are 60 meters apart, and then we've given the gravitational force between them. Okay, we said before, force is the gravity constant times mass of the first object times mass of the second object over the radius, or the distance in this case, between them squared. Let's solve for one of the masses, and we get the same thing we got back in number one. Excuse me, in this case, it's two identical satellites. So m1 times m2 becomes m squared. So excuse me, it's not quite the same. It's almost the same. So m squared is equal to fr squared over g. They gave me the force between them. I know the distance between them, and it's already in meters because that's good. It's going to be squared over the value for g constant. This, excuse me, start here. 60 squared times this divided by this. I suggest you hit pause and actually try it. Gives me this number in kilograms squared. But it's equal to m squared, so I got to square root both sides. Hit the square root button, equals, and see if you get pretty darn close to 3,194 kilograms. Seven, if you weigh 846 newtons on Earth, what's your weight on Mercury's equator? Mercury has a mass of 3.285 times 10 to the 23rd kilograms and is only 2,440 kilometers at the equator. So, this is the formula we're really going to use, but I need my mass. And I was given my weight in newtons, the force of me due to gravity. And I needed kilograms for this because I can't put newtons in for mass. So back to our old little F equals ma, my force or my weight my force due to gravity equals my mass times 9.8 meters per second squared. That's the acceleration due to gravity on me. This divided by that will give me 86.33 kilograms. That's the mass of me. So the force is going to be G, again, times mass of the first object, which I said was me, times mass of the second object, which is Mercury, over the distance between me and the core of Mercury squared. Now, I was given this in kilometers, but stick 3 zeros on it and it's meters. So, I suggest you do this times this divided by this. Excuse me, I said that wrong. This times this times this. Write it down. Square this, write it down. All the top divided by the bottom. The result of the top divided by the result of the bottom. And see if you get 317 newtons or something really close. If Earth's mass were 6 times as great, but its average radius remained the same, what would be its gravitational field G be in meters per second? If the mass were 6 times as great, but I'm the same distance from the core, then my distance isn't going to change. I don't have to pay attention to that. I'm just going to say it's 6 times greater than what I have now. This is my value at the current size of Earth, 9.8 meters per second squared. It's going to go up 6 times. 6 times 9.8. 58.8 meters per second squared. If Earth's mean radius were 6 times as great, so the Earth has grown 6 times, but its mass remained the same, what would its gravitational G value be in meters per second squared? So gravity varies with the square of the radius. And we divide by the radius. So if it goes up, if the radius grows 2 times, the gravity field decreases by 4 times. And if the radius increases 6 times, I'm 6 times farther from the core than I was before. It's 6 times, R is 6 times bigger, but R is squared. So the gravity field is going to be 9.8 meters per second squared divided by 36. And you know what? I forgot to put a value on it. You can figure it out. 9.8 divided by 36, and the units will be still meters per second squared. What is the mass of the sun? Now, I need something that includes, what have I got? I've got the mass of one object. You know what? That's a distractor. The mass of the orbiting object is immaterial to this. I need something that has the time of orbit, which we've got here, the distance from the sun, which is the radius, and that's all I really need because I already know capital G, Cavendish's constant. I got to do a couple tricks first though. T squared, the time of the orbit, is 4 pi r cubed over gm, which is a rewriting of the one we saw before, where it was t satellite equals square root of, it was actually 2 pi times square root of. This formula is a rewrite of this formula. They're the same thing. However, I need this to be in meters for my distances, and I need my time in seconds, or it's not going to cancel out right. So the distance from the sun of Jupiter is 778 million kilometers, but I stick 3 zeros in it. There's 778 million. But I stick 3 zeros on it, and it's meters. Now, I don't want to have to write that in my equation. That's too stinking big. So I'm going to put it in scientific notation. And it's 7.78 times 10 to the 11th meters. Now, I mean, I could put that in, but I don't want to, so I put it in scientific notation. In this case, you must use seconds. The units won't cancel right if you don't, because we're working with stuff like newtons in here, and there's no days in newtons. There are seconds to cancel out in newtons. So 431 Earth days, but there are 24 hours in a day. There are 3,600 seconds in an hour. And that gives me 371,198,400 seconds. That goes in for my time and is squared. Here's my G number, 4 pi. Here's my distance from the sun, cubed. You're probably going to have to go and write down the top number, this cubed, times 4 times pi. Write that down. This squared times this, write that down. This divided by that, see if you get about 1.99 times 10 to the 30 kilograms. Also, I got some goofy answers for 12. Mine is the time for an Earth's surface to point at the same spot in the sky and do a 360-degree turn is slightly less than to point at the sun again, because it has moved in orbit.